We're going to continue with our discussion of three-dimensional functions here today, and this is the part of the unit that I'm most interested in, and that is the derivatives of three-dimensional functions. And we're going to see how a lot of the stuff from 2 dimensions that we talked about here today is going to apply in 3 dimensions as well. Probably by the end of the day here today, we'll be looking at how do we find maximums and minimums on 3-dimensional graphs. And we're going to see that the process that we use in 2 dimensions is exactly the same as 3 dimensions. Okay? All right. But before we can do applications like that, we need to look just at getting comfortable taking derivatives of 3-dimensional equations. Okay? And so let's start with an example like this one right here. Let's see. F of xy equals 3x squared minus 7y plus 8x. Now, one of the things with 3 dimensions is that we have to always specify which derivative we want to take, because we have actually 2 independent variables here. We have x's and y's, and we decided last time that we can only look at one rate of change at a time. We can only look at how is x changing or how is y changing. We can't look at them both at the same time. So here's a little bit of new notation that we'll have to introduce here today. If I want to look at how x is changing, I'm going to write f with a subscripted x, saying that I want to take the derivative of this function with x being the variable. Okay? Now, when I take the derivative with x as the variable, that means that I'm going to let the y's, I'm just going to treat y like it's a number. Okay? So let's start with this. If I wanted to take the derivative of this and x was the variable, what would the derivative be? 6x, right. Just normal derivative, exactly like we've been doing in the past. Okay? Now, if y is a number, y is a constant number, and if I multiply it by 7, what would its derivative be? It would be 0, because y is a number. I'm not letting y change, I'm fixing it. So if y was a 2, this would be a 14, the derivative of 14 would be 0. If y was a 3, this would be 21, the derivative of 21 would be 0. So y is a number, so this derivative is just 0. Okay? And let me tack on a y up here at the top. Okay? I want to make that 8xy up here. Okay? What would be the derivative of 8xy? Okay? Now, initially, we would say, oh, we probably need to do a product rule here, but we really don't. Because how many variables do I have in this expression here? I only have one variable. X is my variable. I'm going to let y just be a constant number. So what would be the derivative of something times x? Wouldn't the derivative just be the something? If I had 10x, the derivative would be 10. So what's the something in here? Well, 8 is part of it, and then y is part of it, isn't it? Okay? If y was 10, then I would have 80 times x. That derivative would be 80, or in other words, 8 times 10. Okay? So the only thing is, when we do what these are called partial derivatives, whenever we do partial derivatives, we have to remind ourselves which letter is the variable and which letter is the constant number. Okay? All right. We can also do the derivative of this thing with respect to y. So now what if I want to switch this around? I want y to change, and I want x to stay the same. Okay? Well, let's see how this one works. Okay. X is a number, and y is a variable. So what's the derivative of 3x squared? 0, because I don't have any y's in this expression, do I? So nothing is changing, so this derivative is 0. All right. What's the derivative of negative 7y? Negative 7. All right. And what's the derivative of 8xy? 8x. Very good. Okay. Because the y is the variable, and so if we kind of think about it as some number times y, the derivative would just be the number, 8x. Okay? And these are, like I said, these are called the partial derivatives with respect to x and with respect to y. Okay? Let's look at some more examples. What if we have this expression? F of xy is 3 times e to the 2x plus y. Okay? We can do the same thing with exponential functions, taking partial derivatives. All right, again, the thing is, I have to remind myself which is the variable and which is the constant number here. Well, in this case, x is going to be the variable, and y will be the constant number. So the first question is, what's the derivative of 3 times e to all this power? 3 times e to all that power, right. The derivative of an exponential, it basically just rewrites itself. Okay, that's part of the derivative. Now I go up and look in the exponent here. I look for the chain rule. Okay, so now if I just think about 2x plus y, okay, if x is the variable, what's that derivative? It would just be 2, wouldn't it? The derivative of 2x would be 2, and the derivative of y would be 0 because y is just a number. So this derivative would just be 2. Okay, and so if we were going to simplify this answer, we would have 6 e to the 2x plus y. That would be our derivative. Okay. All right, what if we look at this in terms of y? What is the derivative of this function if we let y be the variable? Well, first of all, what's the derivative of 3 e to the 2x plus y? If we just look at it as a whole, 3 e to the 2x plus y, right, stays exactly the same. Okay, the derivative of an exponential is itself. Okay, but now we have to look inside the exponent here. What's the derivative if y is the variable from the exponent, from the chain rule? Just be a 1, right. The derivative of 2x would be 0, because that's just a number, and y's derivative would be 1. Right. So this is just multiplied by 1. So actually, the derivative with respect to y was exactly the same as the original function, because the chain rule just gave us a 1. Okay. All right, so there's that example. Next example. Let's see, I'll move over to here. What if we've got natural logarithms? Natural log 1 plus 3 x squared y cubed. Okay. And again, let's let this be a function of 2 variables, and let's start by taking the derivative with respect to x. Okay? What's the derivative of the natural log of something? Natural log's derivative was 1 over the something, right? Yeah, so I got 1 over all this inside the absolute value symbol. Okay. Now I have to multiply by the chain rule, and the chain rule says, well, now we're done with the logarithm part of the derivative. Now let's just look inside here, and let's figure out what the derivative is in here. If x is the variable, what is my derivative in here? 6x and a little more, y cubed. Okay? And the reason it is, okay, first of all, y cubed is just a number because y is not being allowed to change in here. So y cubed is just a number, so it stays there. Just kind of like the 3 stayed there, and then we had a 2x for our derivative on here. Right? Okay? So this would be our answer. We could rewrite it as just one fraction if I move this chain rule piece up here to the numerator. Okay? But it's not really necessary. All right, what if we look at the derivative with respect to y? Okay, well again, what do I get from the natural logarithm part? Yeah, just 1 over. Okay, so this stays the same. Question will be, how does the chain rule get affected? Because now we're letting y be the variable. Okay, does the 3 just stay there as part of the derivative? Yes. Okay, does the x squared just stay there as part of the derivative? Yes, because x is a number this time. Y is the variable. And then what's the derivative here for y cubed? 3y squared. So I can either write 3y squared, or I can just change this over to a 9 from 3 times 3. Right? Okay? All right, let me see if there's any other examples we want to go through. Yeah, let's do this one right here. 3x squared y up in the numerator. And in the denominator, we've got e to the xy plus 2. Okay. And again, our goal is let's find each partial derivative. Okay. All right, now this time I think we're going to have to use the quotient rule. I don't think, like over here I had mentioned in an earlier problem that we wouldn't have to use the product rule in that situation because there was only one x and one y in the whole problem. Okay. Well, here I've got multiple x's and multiple y's, and they show up in both numerator and denominator. So I'm going to need, no matter which one I let be the variable, I need to do the quotient rule on this one. Okay? So let's run through the quotient rule. What does it say I need to start with? Bottom times the derivative of the top. And what's the derivative of the top if x is the variable? 6xy. Good. Okay, minus the top times the derivative of the bottom. Okay, x is the variable. What's the derivative of this? E to the xy. Derivative of an exponential is just itself. Now if I go up and look in the exponent, what's the derivative of xy if I let x be the variable? Y. Good. Okay, because y is a number. So if this was 3x, the derivative would just be 3. Okay, so yeah, whatever the y is, that's what the derivative will be. Good. Okay, and then of course the derivative of 2 is 0, so we don't have anything with that. All right, and then all divided by the bottom piece, quantity squared. Okay. Now, as far as simplifying on this, I don't think it's really that necessary. I mean, there's not going to be really too much of an advantage to trying to clean this up. There's really not a whole lot that factors because these terms don't look the same, so I wouldn't spend any time really simplifying on this. Okay? All right, let's go after the derivative with respect to y. Okay? All right, again, we start with the quotient rule, so we start with the bottom. Okay, what's the derivative of the top this time? 3x squared, okay, because I've got something times y, so the derivative would just be the something, all right, the 3x squared, okay, minus the top times the derivative of the bottom. Derivative of this would be what? E to the xy times x, good, because the derivative, if y is going to be the variable, whatever's in front of that y will be my derivative. And then all again divided by the bottom squared. Okay. All right. Any questions with taking partial derivatives at this stage? Okay, because this is our first step in this process that I talked about a little bit ago. If we're going to try to find maximum and minimums, okay, well, let's just talk about it right now. How did we find maximums and minimums on two-dimensional graphs? What was our process for doing that? If I wanted to find a maximum on a parabola, how did we use calculus to do that? We took which derivative? First derivative and set it equal to what? 0, because we wanted a 0 slope. Okay? Well, in 3 dimensions, that concept is exactly the same. If we want to find the minimum value, last time we had what's called a paraboloid. It was a parabola in the one direction, and then it was a parabola in the other direction. It looked like a bowl almost. There's definitely a minimum value on that paraboloid. If we want to find that value using calculus, okay, what we need to do is we need to take the derivative with respect to x, and we need to take the derivative with respect to y, and guess what we want to set those equal to? We want to set them equal to 0. What this is really saying is, if we want to find the minimum, we need to have a 0 slope going in this direction, and we also need to have a 0 slope going in this direction. And if both slopes are 0 in both those directions, then we would have a minimum value. Now, I don't think we want to do that with this equation because this is getting pretty messy here. If we tried to set this equal to 0, it would probably take us a while to solve it. But when we get to more manageable equations, that will be the process we use. We find both partial derivatives and we set them equal to 0 and try to find the solutions. Okay? So it's very similar to what we did before. Okay? All right. There's one more skill that we need to talk about, though, before we can start setting functions equal to 0 and trying to solve. Because there's one more piece to the puzzle here that we will need. And that's going to be called second-order partial derivatives. And what second order derivatives are, basically we're saying we're going to take the second derivative of a three-dimensional function. Okay? So just like we could do second derivatives before with two-dimensional functions, we can do the same thing with three-dimensional functions. Now, let's start with an example that'll be a little more manageable, though. Okay? F of xy equals 6x cubed times y minus 9y squared plus 2x. Okay. When we take second order or second derivatives, okay, before we can do that, we always have to take the first derivative. So let's start with that. Let's start with what is f sub x? What's the derivative of this function with respect to x? Okay, so what's the derivative of this with x being the variable? 18x squared y. Okay, the y is a constant, so it just stays in there. The derivative of this with respect to x? 0. The derivative of this with respect to x? 2. All right, so here is f sub x. Okay, let's also calculate the derivative with respect to y. Let's get all the first derivatives taken care of, and then we'll go to the second derivatives. Okay, all right, what's the derivative of this with respect to y? 6x cubed. Derivative of this with respect to y? Okay, minus 18y, and this with respect to y is 0. Okay, so we've got our first derivatives taken care of. All right, there's going to be lots of options for second derivatives, okay, or for second order partials, because we've got lots of combinations possible. One of the combinations is I could take the derivative of this function with respect to x again. You know, I took the derivative with x the first time. I could take the derivative with respect to x again. Okay, so let's do that. Okay, if I look at this function, what's its derivative with respect to x? (36) xy. Good. Okay, because the x will, the squared term will go down to x to the first, and then the y is a constant number, so it just stays there. Okay, so 36xy, and the derivative of 2, of course, is 0. So this is the second order derivative with respect to x. In other words, we took the derivative with x, and then we took the derivative with x again. Okay, now, there's another option that's available, and that is if we take the derivative with respect to x the first time, and then we take the derivative with respect to y the second time. And you might wonder, why would you ever want to do this? Well, again, as we progress through this concept, we're going to see that there's a place for both of these when we're trying to find maximums and minimums. Okay? All right, so what if we look at this function, and we take the derivative with respect to y this time? What do we get? 18x squared. Good. Okay. All right, so we've got both partial derivatives with x being the first derivative, and then we did x and then y. Okay? Now, what other partial derivatives could I come up with? What else could I come up with besides these two? I could do fyy. Sure. Okay, I could take the derivative of the y function with respect to y again, and then what's the last one? There's one more. fyx, right. Okay, I could take the derivative with y the first time and derivative with x the second time. Okay, so let's go ahead and calculate both of these. All right, what's yy here? So I look at the fy function, and I take the derivative with respect to y again. Okay, this is 0, this is negative 18, isn't it? Okay, so this is just simply negative 18. And then what's fyx? All right, so I look at this function, and I want to take the derivative this time with respect to x. 18x squared. Okay, now, anything that you notice on those four partial derivatives? xy and yx came out to be the same answer. And so that raises the question, will that always happen, or was that coincidental? Okay, and the answer is, for all the functions that we will be doing in this semester, these two values will be equal to each other. fxy and fyx will always be the same. So even though there's really four different derivatives that you could calculate when they tell you to find all the second order derivatives, okay, you really only need to do 3 of them, because you only need to do one or the other of these, because they'll give you the same answer. Okay? All right, very good. Let's look at another example of finding second order derivatives. All right. right, let's see. Z equals negative 3y times e to the x. Again, we don't want to get too complicated because when we start getting into second derivatives, you probably remember from 2 dimensions, they can get nasty pretty quickly here. Okay? So we just stick with pretty basic ones. All right, notice my notation that I was using over here, fx, fy, fxx, and so forth. We can do something similar over here. This is just z, so if I wanted to take the first derivative, I would just write it this way. I'd write z sub x, the derivative of the z function with respect to x. All right, so what is the derivative of this function with respect to x? What is, now all of this is just a number, right? Because x is the variable. So what happens if we have a number in front of e to the x? That number just stays there, doesn't it? Okay, so the negative 3y will just stay there. And then what's the derivative of e to the x? Just e to the x, right. So this derivative is just exactly the same as the original function. Okay. Now, I kind of have a chain rule, but the derivative of up here is just what? It's just 1. So I kind of got a chain rule, but I don't have to write it. Okay, what's zy on this one? Okay, definitely the negative 3 will stay there. What else? The e to the x will stay there because that's also a constant, and the derivative of y is just a 1, isn't it? Okay. You know, if I was to rewrite this, I could rewrite it this way. Okay. I've got all of this stuff times y, and the derivative of something times y is just the something. Okay. So just negative 3 e to the x. All right. Now, the thing we're really after, though, we really want the second order derivatives. Okay. So let's calculate zxx. So what's the derivative of the x function with respect to x again? Same thing, right? Okay, the derivative of negative 3y e to the x, if x is the variable, it just is another exact copy of itself, right? Okay, all right. What is zyy? So I look at the zy function and I take the derivative with respect to y. We haven't had one of these yet today, but this will show up eventually in your problems. Do we have any y's in this thing? No. So the derivative is 0. This is just all a constant number. The derivative of any constant number is just 0, right? So since there's no y's in here, the derivative is just 0. Okay, good. And then what about zxy? And again, you can look at it either way. You can look at either one of these functions and then just take the derivative with respect to the opposite variable. Okay? So like for example, if I look at zy, then I would take the derivative with respect to x. So what's the derivative with respect to x here? Same thing, right? Negative 3 e to the x. Right. Okay? If I look at this function, if I look at the zx function, I can take the derivative with respect to y. The derivative with respect to y is just negative 3 e to the x, right? Because the y to the first is just it's kind of like a linear function almost. Okay, so here's our 3 second order partial derivatives. All right. Okay, now let's start getting into setting these things equal to 0. Let's start looking for maximums and minimums on 3-dimensional graphs. Okay, we've got 9xy minus x cubed minus y cubed minus 6. Okay. We want to find out where we have a possible maximum or minimum. And the concept or the procedure that we will use is to take both of the first derivatives and set them equal to 0. Okay, so let's just see how this works. All right, so what's f sub x first of all? All right, what's the derivative of this if x is the variable? 9y. Derivative of this, negative 3x squared. Derivative of this, 0, and negative 6, 0. All right, so here's my first order derivative with respect to x, and here in a little bit I'm going to set this equal to 0. Okay, what's fy on this graph, or this equation? 9x This is 0. Minus 3y squared. Okay, and again, we want to set that equal to 0. Okay, so we've got what we've got here, and this is where, again, college algebra comes into play, is that we've got a two-dimensional system. We've got two equations and two variables, and we need to solve for both x and y in this setup. Okay, does anyone have any good ideas for ways to solve for either x or y? There's more than one possibility here. Okay, we've definitely got factors of 3 in both of these equations, right? And so we could definitely factor out a 3 and divide that off. 0 divided by 3 would be 0. Okay, so we can definitely do that. Let's go ahead and start with that. Okay, if I go ahead and factor out a 3 and then divide it off. So I've got 3y minus x squared equals 0. Right? I just factored out a 3 and then divided that off. 0 divided by 3 is 0. Okay? I can do the same thing in the second equation. 3x minus y squared equals 0. Okay, so that's a little better start. Okay, what do we want to do next? I might recommend take one of these equations. You know, they're kind of symmetrical almost, so it doesn't really matter which one. Let's just add one of these, like add x squared over to the right side, or maybe add y squared over to the right side. Let's just move some variables around here. Okay, so we've got 3y equals x squared, and 3x equals y squared. Okay, what I'm going to have to eventually do is to solve one of these equations for, like this first equation, solve it for y, and then sub that number into the second equation. This is what we called substitution in college algebra. Okay, so let's go ahead and do this. If I solve the first equation for y, I would just get x squared divided by 3. And if I take that and sub it into the y equation down here, okay, then I should be able to reduce everything back to just one variable. Right? So I'll have 3x equals x squared divided by 3 quantity squared. Okay? This is how I eliminate one of the variables, is I just solve for one of the equations and sub it in. Okay? All right, now we're going to need to go ahead and let's move up here. Okay? But let's go ahead and solve this right side here. Okay? What is x squared squared? X to the 4th. And the denominator, what's 3 squared? 9. Okay, so this is just x to the 4th divided by 9 if I clean it up like that. Okay, what would you do next if you were trying to solve for x? What could I do with the 9? Okay, multiply it across, sure. Okay, 27x equals x to the 4th. Next thing I probably want to do is just move everything over to one side and set it equal to 0. Okay, because now once everything's over to one side, what can we do again? Factor again, right. Okay, what can I factor out of this? Take out an x, and I've got x cubed minus 27 left over. Okay, so what's one of my possible solutions here? X equals 0. And what's my other solution? Well, you might be able to figure this out in your head, but if I was to set this factor equal to 0, so x cubed minus 27 equals 0, you add 27 over, what's the other solution for x? Cube root of 27, which is 3, right? Okay, so the other possibility here is that x equals 3. So what this is saying is that right now, there's two possible values of x where we could have maximums and minimums. You know, one of them might be a maximum, one of them might be a minimum. Okay? But we've got two possible places we've got to consider. Now, the other thing is, though, we can't just stop here because we not only need to know the x coordinate, but we also need to know the y coordinate. Okay? So if x is 0, okay, if I come back over here into any of these simplifications, if x is 0, what is y? 0, right. Okay, this looks like the easiest one to work with. Okay, 0 squared over 3 is 0. So it looks like if I go to 0, 0 for x and y, that looks like it's a possible location for a maximum or a minimum. Okay, what if I let x equal 3? If I come back over here, what's the y coordinate? It happens to be 3, right, because we get 9 divided by 3, which is 3. This is pretty coincidental, in the fact that these numbers are turning out to be exactly the same. Now, as you look at the initial equation, can you kind of tell anything about why we're getting mappings, 0, 0, and 3, 3? What do you notice about the equation? Okay, doesn't it have a lot of symmetry in it? Here I've got an x and a y in the same function. They're both raised to the first power. I got a negative x cubed and a negative y cubed, so those are basically the same thing, right? That's why we're getting these numbers to come out to be the same. That won't happen in every equation. Okay? All right. The last thing I want us to do, we've got these points here, 0, 0, and 3, 3. The next thing I want us to do is figure out, well, what's the y-coordinate at those points? So we figured out where the x's and the y's were, but I said it wrong. What's the z-coordinate at these points? What's the third coordinate? If I sub in 0 and 0 for x and y, what do I get for an answer here? Negative 6. So 0, 0, negative 6 is a possible location for a maximum or minimum. Okay? What if I sub in 3's in both spots? Okay, 3 times 3, 9. 9 times 9, 81. Okay, minus 3 cubed. Be 27, right? Okay, minus another 27, and then minus 6. 54 and 6 would be 60. 60 off of this would be 21, right? Okay, so it appears that these are the two places on this particular graph where we've got either a maximum or a minimum. Okay? Now, how can we decide if this is really a maximum or a minimum? It appears that this is a minimum and this is a maximum just because one's negative, one's positive, but that's not necessarily always the case. We have to be a little careful. Well, one way that we could check this, and I'm going to start with this first one here. What if I change the y-coordinate just a little bit? I'm at this 0, 0, negative 6 spot on the graph. What if I move a little bit in the y direction? Okay, I want to see, does this z-coordinate get bigger or smaller? Okay, because that'll help tell me if this is a maximum or a minimum. All right, so let's look at this. What if I put in 0 and 1 into this function? Okay, I put in 0 for x and I put in 1 for y. So 0 for x, that's 0. That's 0. What if I put in 1 for y here? Negative 1 minus 6, so negative 7. Okay? So what does it appear is happening here? If I go a little bit in the y direction, if I move a little bit to the right in the y direction, what happened to this value? It got smaller, didn't it? So what do you think that means that this might be? It might be a maximum, right? Because as I moved a little bit off of that point, I got a smaller value. So that means this is a higher number, so this might be a maximum. Okay, now, the other thing we want to look at, though, we also want to check, well, what if I go in the other direction? What if I go to the left 1 unit? Is this still a higher number than this one? Okay, well, let's try it. What if I sub in negative 1 over here? Well, that's 0, that's 0. What do I get on this one? Negative 1 cubed is negative 1, and then I got this negative, so it's positive 1. Positive 1 minus 6 is negative 5. Okay? So this tells us something in the fact that, is this really a maximum value at that point? No. Okay? Because one of the cases, or one of the times, on one side of the graph it was getting smaller, and on the other side of the graph it was bigger. Okay? So kind of what we've got here is we've got, if I just go back to two-dimensional graphs, okay, we've kind of got a situation like x cubed. And the fact that, do we have a slope of 0 right at this point here in the middle? Is that a 0 slope right in the middle? And the answer is yes. If it's really x cubed, it's got a slope of 0. But is this a maximum or a minimum? Well, no, it's neither one. Okay, and that's apparently what's going on with this point here. It's not really a maximum or a minimum. Okay? All right. Let's investigate the other point, though. Let's check 3, 3, and let's see if we get anything off of it. Okay? So what if I go from 3 up to 4? Okay, what if I change that y-coordinate to 4? Well, we could investigate that and just see how that value is related to 21. Okay? So let's see, why don't this half of the room, go ahead and plug in 3 and 4 into that equation and tell me what you get. And then the other half of the room, What's the other point that we would want to investigate here? 3, 2. Let's look in the other direction and see what's happening. Right. Okay, so this side plug in 3, 4, and the other side plug in 3, 2. Tell me what you get when you sub into the original function. Okay, what about for this one, 3, 4? $11? And what about for 3, 2? 13? Okay. Now, as we look at these two situations here, or these two values, okay, both of these numbers are related how to this one? Well, they're both smaller. So that means as I look at it coming from one direction, I'm smaller. And then I hit this peak of 21, and then I also get smaller on the other side. So it appears that 3, 3 could still be a what? Could still be a maximum, right? Because it's smaller in this direction, and it's also smaller in this direction. Now, the thing is, though, in 3 dimensions, just checking this is not going to be sufficient for determining if something's a maximum. Okay? Because it could be a maximum in the y direction, but maybe we've got a graph where it's a minimum in the other direction. So the thing is, I changed the y coordinates a little bit in both directions. I would also want to go back and consider, what if I keep the y coordinate at 3, and what if I start changing the x coordinates a little bit? So what if I change this to 4 and this to 2? And I'd also want to check to see, are both of those numbers smaller than 21? See, that's the thing in 3 dimensions. We've got to check every direction to make sure that these numbers are all smaller. Okay? My guess is that when we plug these in, just because of the symmetry of that graph up there, I'm guessing we're still going to get 11 and 13 right here. Okay? Just because of all the, everything looks the same for x's and y's in this graph. So my guess would be that yes, this 3, 3, 21 really is a maximum value. Okay? Because we see that if we look in both directions, that it's higher than any of the other z coordinates coming no matter which direction we're coming from. Okay? All right, any questions with that? Okay? Now, what we're going to find out here, and we won't get to it today because we're going to be out of time here in about 10 minutes or so, but we're going to find out next time that there's a little bit more efficient way to check. If I get to this point and I see 0, 0 is a possible maximum or minimum, there's actually a better way to check to see a maximum or a minimum than going through and plugging in all these points. Okay? But I wanted to start today with this because this gives you a little bit of an understanding of this is really what we're looking for. Okay? But next time there's a little bit of a process that involves second derivatives that can tell us if 0, 0 is a maximum, a minimum, or actually something else that we'll talk about next time. Okay? Let's do another example of finding out where we have possible maximums or minimums, so that way when we do start next time that we're ready to learn that new process, we can kind of finish off this whole thing here. Okay? So let's look at another equation. Let's see here, which one do I have picked out? We've got r of xy equals 4x over x plus y. And we want to find out where this graph has possible maximums and minimums. Okay, now we got to be a little more careful on this one. We got a little bit of domain problem down here. If we ever got 0, 0, we'd have to throw it out because that'd be division by 0. Okay, so we'll have to watch that just a little bit. All right, start off with, what's the derivative of this function with respect to x? What's r sub x? Okay, well, which rule do I have to use here? Quotient rule, right, because I got x's in both spots, so I need to do quotient rule here. Okay? All right, so I take the bottom piece times the derivative of the top, which is 4, minus the top times the derivative of the bottom, which would just be 1, right? The derivative of x would be 1, the derivative of y would be 0. 1 plus 0 is just 1. All divided by the bottom piece squared, and eventually we'll want to set that equal to 0. Okay? All right, what's r sub y? Okay. I really don't have to use the quotient rule here because I've got only one y in the whole problem, but I think it'll be just as easy if I do use it. Okay? So I start out with the bottom. Now what's the derivative of the top this time? Just 0 because there's no y's up in the numerator. Minus the top times what's the derivative of the bottom? Y is the variable. The derivative of x is 0. The derivative of y is 1. So this is just a 1. All divided by bottom squared. And again, I will want to set that equal to 0. Okay? All right, as I look at these, if I clean up this numerator here, what's the only thing that's left? It actually simplifies quite a bit. Just a 4y, right? Because I got a 4x minus a 4x. That goes away. The only thing left is 4y. So really what I've got here is 4y over x plus y squared equals 0. Now, if we ever want to set a quotient equal to 0, what's the only thing we have to worry about? What's the only piece that really needs to be 0? The numerator, right? Because 0 divided by anything is equal to 0. So really I can ignore this denominator, and then what's the value I get? I get y equals 0. Okay? So from this first equation here, I figured out that y has to be 0 if I'm going to get a maximum or a minimum. Okay? All right. If I come down here to the second equation, okay, again, a lot of stuff simplifies. All this is just 0. And so do I need to worry about denominator again? No. So I can ignore that. So I get all of this, and what's x? X is 0, right. Okay? So this one actually simplified so much. I didn't have to do any algebra like I did over here. I didn't get two equations that had x's and y's in them. I just got straight to the answers on this one because it just simplified so much. Okay? Now, 0, 0 on this example, is that a good place to look for a maximum or minimum? No, why not? Because it'll be division by 0, won't it? Okay? So what does that tell me if I solve all this and I get 0, 0 and that's no good? What does it mean about this particular graph? Well, it just means that this particular graph will not have any maximums or it will not have any minimums. Because the first derivative is equal to 0. The one value that we could, that actually worked, was not going to work because it gave us division by 0. Okay? All right, so again, that's a possibility. We saw that in 2 dimensions. Certain functions just don't have maximum or minimums, and that's what happened here. Okay? All right. I want to look at one word problem here. Let's see if I can get it up on the screen. And the projector is going to take just a minute here to warm up. Okay. Well, maybe I can get over to number 45 here. Well, let's go down. Let's just do 46 because I think it'll stay on the screen better here. Okay, 46. The revenue from the sale of X units of a tranquilizer and Y units of an antibiotic is given by this. So we have 2 different things that we're selling. That's why this is a 3-dimensional graph. I can sell as much of X as I want. I can sell as much of Y as I want. And I can get a revenue by the time I'm finished. Okay. All right, it says suppose 9 units of tranquilizer and 5 units of antibiotic are sold. A, what is the approximate effect on revenue if 10 units of tranquilizer and 5 units of antibiotic are sold? Okay, now, I need to talk to you about the calculus part of this question here. What are we wanting to change? Are we wanting the x to change or the y to change? We're going to go from 9 units of tranquilizer up to 10 units of tranquilizer. Well, as we look up here, which one was the tranquilizer? Well, that was the x, right? So we want the x to change a little bit. So what derivative do you think that they're asking us to find here in 46 letter A? Well, they want the partial derivative letting x be the variable. Okay? So that's how we decide that. Okay? So let's go ahead and do that. I'll move this over so it doesn't fall down again. So we're going to take this revenue function, r of xy, 5x squared, 9y squared minus 4xy. And we're going to take the derivative with respect to x because they wanted the x to change a little bit. We're going to go from 9 to 10. Okay? All right, so what is my partial with respect to x? 10x, 0, and minus 4y. Right, okay? So here is my partial derivative. Now, if I come in here and I substitute in the values that I started with, if I plug in 9 and 5 for the number of tranquilizer units and the number of antibiotic units, if I sub those numbers in, let's see what we get. Okay? If I sub in 9 here, I get 90. I sub in 5 here, I get 20. So the answer is what? Is 70. Okay? So what this is saying is that around, when I'm selling about this many units, if I let the x change, in other words, if I let it go from 9 up to 10, I can expect to see my revenue increase up to around $70. Okay? My label for this, okay, remember this is a derivative, so this is kind of like a dr dx almost type label. My label would be in dollars per x is unit of tranquilizer, right? So this would be $70 per unit of tranquilizer. Okay? In other words, if I let the tranquilizer go up to 11, so what if I go from 9 to 11? Approximately, what should this answer be then? Well, it would be 140, right? Because I would have 2 units. Okay? So it would go up twice. It would go up $70 and another $70. Okay? So that's just a rough idea. Now, just to convince you that this is pretty close to correct here, okay, what if we actually go ahead and just in the original function, what if we calculate r of 9,5 and then we calculate r of 10,5? What if we actually let it go up to 10? And if we subtract those numbers, does that get us really close to 70? Well, let's just see real quick. Okay, again, let's split up the room here. This half the room, sub in 9 and 5 into this original, and the other half the room, sub in 10 and 5 into the original. And tell me what you get for an answer. Okay, what do we get for 9 and 5? $450? Okay. I'm going to say that that's good unless somebody disagrees with it. Okay, what about for 10 and 5? $525? Okay. I'm going to suspect that those are right because how far apart are those two numbers? They're 75 units apart, so the actual change in revenue is $75, but if we just use a derivative, does this give us a pretty close approximation? And the answer is yes, okay, that this is really close to $70 per unit. Okay, very good. We'll continue with this partial derivative some more next time.